Okay. Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 53 of this seminar. Today we have two excellent speakers, Pierre Lissy and Takeo Takahashi. Introducing Pierre Lissy, we have to Professor Mauricio Santos. Thank you, Mauricio. You can start.
Thank you, Juan, and thank you, Pierre, to have accepted give this talk in this seminar. Professor Pierre Lissy is a young researcher that made his PhD at Pierre Marie Curie University under the supervision of Professor Jean-Michel Coron in 2013. And nowadays he is associated professor at Paris Dauphine University, and he's the author of many outstanding results in control of PDEs, having developed many techniques and methods in control, and some of them are connected to other fields of mathematics. And what can I say is that there are a lot of very important results in the fields, and which are published in many renowned journals. So Pierre, thank you very much again, and he will talk about today. He will talk about a non-controllability result for the half heat equation on the whole line based on the prolate spheroidal wave functions and its applications to the Grushin equation. Pierre, please.
Okay, thank you very much, Mauricio, for the introduction, and I would also want to thank the organizers for the kind invitation. So today, as you can see, the title is quite long, but what I will do is that I will present a non-controllability result for two equations. The first one is the half heat equation and the Grushin equation. So in fact, the result in itself is not very surprising, but what I find interesting in this work is in fact the method. So here is the outline of the talk. So I will start with giving some general introduction, in fact, about control theory and also some uncertainty principle in harmonic analysis. Then I will give the definition on some properties of the prolate spheroidal wave function. That will be the core of the talk. Then I will present my non-controllability results on the half heat equation, and to conclude, I will give some hints on what is happening for the Grushin equation. Okay. So first of all, I would like to recall a little bit of basic linear control theory. So here, what we consider as a system is a linear system. Y prime is equal to AY plus BU. So A and B are linear operators. And here you have some state Y, and you're also given a parameter U that is called the control. And the control, in fact, gives you some additional degree of freedom to try to act on the system. So for instance, you can think on of the heat equation. So if you take A to be the directly Laplace operator on a bounded domain capital omega, and B can be, for instance, the characteristic function of an open subset little omega of your big domain. And so there are many questions that you can try to answer in this setting. And here what will interest us, in fact, is the notion of null controllability. So the question is, if you are given some initial condition y0, can you find some control such that you can bring, in fact, your state y to 0 in time capital T? So here you have, in fact, an existence problem because you need to construct the control. But in fact, since we are in a linear setting, you have an equivalent reformulation, which is in fact very useful. You just introduce the adjoint system. Z prime is equal to A star Z with an initial condition, and you can prove with basic tools of functional analysis that controlling the system to 0 is equivalent to what is called an observability inequality for the adjoint system, which is written in green here. So what does it mean? It means, in some sense, that you can recover the final state Z of capital T thanks to what is called the observation. So here, what does it mean? It means that if you observe your system on 0t times little omega, then you are able to recover the state, the final state Z of capital T. And so here, what is very interesting is that with this duality argument, you have changed the problem. You don't have a problem of existence of the control, but you have a problem of uniqueness on an equation which is free, in the sense that here you don't have any control. Okay, and so you see that in fact this is some kind of, let's say, quantification of a property of unique continuation, because if B star of Z is equal to 0, then Z of capital T is equal to 0. And for instance, for the heat equation, since you have a backward uniqueness, it means that in fact the whole solution is equal to 0. Okay, so this is some kind of quantification of a unique continuation property. Okay, so now I would like to speak a little bit about one precise uncertainty principle. So what is an uncertainty principle in harmonic analysis? This is, in fact, a mathematical principle that formalizes the fact that it is possible for a function and its Fourier transform to be simultaneously concentrated. And of course, concentrated, you need to give precise meaning to that. And here, concentrated will be, in fact, understood in terms of support. So here I give a trivial example of an uncertainty principle. If, which is very well known, if you take a L2 function, which is such that f and its Fourier transform have compact support, then f is equal to 0. And in fact, the proof is very simple. Since f is compactly supported, you have this expression for the Fourier transform, but as soon as you have this expression, you can, of course, extend it to the whole complex plane. So the Fourier transform of f is an entire function, but it is compactly supported, so this is equal to 0. So, and in fact, you can also quantify this uncertainty principle by an inequality, and it was done in an article by Heimrein on unbooted model. Okay, so here, what I will introduce is another uncertainty principle, which is called the Logvinenko-Sereda uncertainty principle. So here, what we do is that we consider a spatial set S and frequency set sigma, and I will say that this is a strong annihilating pair if you can find some inequality like that, which is true for any function in L2. So you can control the L2 norm everywhere, thanks to the L2 norm of the function outside of this set S and the L2 norm of the Fourier transform outside of this set sigma. And here, for what we'll do in the next part, we just need to consider sigma to be some ball. And then if you consider band-limited functions, meaning that you take functions such that the Fourier transform is supported in this ball, then, of course, this term disappears. And so you have some inequality like that. And this kind of inequality is called a Logvinenko-Sereda uncertainty principle. And so you see that it is some, so what does it mean? It means that if f is supported in S, then f is identically equal to 0. Okay, so this is some kind of quantification of this property, but with some sets that are not necessarily compact. So now the question is, what are the set S and sigma that can satisfy this kind of, what are the set S that can satisfy this kind of inequality? And this is exactly, in fact, they are known. We have a characterization of this set. So here I give two definitions. The first definition is what I will call a thick set. So in some sense, you see that a thick set is something that is quite well distributed everywhere on RD, okay? So if you take the intersection of little omega with some ball with an appropriate radius, and any ball, in fact, that can be centered everywhere, then you still have some measure that, in fact, here you have some uniform constant. Okay, so it means that it is well distributed everywhere on the space. And you have an equivalent definition, in fact, that I will call a Poisson set. So I will say that capital omega is a Poisson set if, when I consider, in fact, the semigroup associated to the half-fit equation, in fact, because this is exactly what I will call afterwards the half-fit equation. half because here, if you put norm of size square, this is exactly the heat equation. And so what I call here absolute value of nabla is exactly the operator which is defined in the Fourier variable like this. Okay, and so I say that capital omega is a Poisson set if you take as an initial condition the characteristic function of this set, and that you let it evolve in some time t, then it is bounded from below. Okay, and in fact you can prove that if it's true in some t, in fact it's true for any t, but it's not very important here. But what is important, in fact, is that you can prove that a set is thick if and only if it is a Poisson set. So it's not very difficult. It's just direct computation. It's not difficult. And what is interesting is that, in fact, you can prove that the set S satisfies a log-Viennese-Sarada uncertainty principle, meaning that you have this inequality if and only if RD, if and only if, in fact, the complementary of S in RD is a thick set. Okay, so it means that, of course, a thick set is quite big. So you expect that you need this set to be quite big for this inequality to be true, and the characterization is exactly that it has to be a thick set. So in fact, I will give a proof of this of the interesting part, in fact, of this of the theorem. So I will prove that if the complementary of S in RD is a thick set, then the log-Viennese-Sarada uncertainty principle are true. But in fact, the proof has an important drawback, is in the sense that you cannot find, in fact, the optimal constant here, which will be very important in the rest of the talk. So how does it work? So it's quite simple. So I will just give the proof in dimension 1, but in fact you can make exactly the same proof in any dimension. So you take a band limited function in -c, and the first thing you do is that you multiply it by some complex exponential. So now it is supported in R+. So this is exactly what is called, in fact, a function in the Hardy space H2 of C+. And for this kind of function, you have, in fact, what is called a Jensen inequality. Of course, there are many Jensen inequality, but one of the Jensen inequality is, in fact, for the function in the RD class. And so you have this kind of inequality. So if you take the logarithm of, so in fact, here, this is exactly the complex extension of G in the upper half plane. And so what you say is that the logarithm of the absolute value of this is less than so you apply it should be a nabla here. You apply the half fit operator to the logarithm of G. Okay, so the next step is just to remark that if you multiply f by a complex exponential, it doesn't change the L2 norm. And so you can prove this kind of inequality, in fact, just by using the fact that the support of G hat is included in this interval 0 to C. Okay, and now, of course, what you can do. So you see that now what you do is that you take the exponential, here, and then you take the square. And so what you obtain for the moment is this kind of inequality. And then you use the Plancherel theorem here. And the next step is to use what is called the theorem on two constants of Göring, which tells you the following thing. If you take a probability measure on R, and if you take a measurable set such that this kind of property is true, then you can prove that there exists, that in fact you have this kind of inequality. And in fact, it's very easy to prove. You just need, in fact, to use 2 times the concavity of the logarithm and to use some older inequality. And so, of course, you will need to apply it to some probability measure mu. And what we will do is here that, in fact, you will take the Poisson measure, because the Poisson measure, it's exactly the kernel associated to the half-fit equation. Okay, so this is what is written here. And so if you use now step 4, so here you have this quantity in green, which is exactly this quantity. And so you have exactly this inequality. And you see that now you just need to divide on the right by this quantity, and then you recover your Ludwig-Sereda uncertainty principle. And because, in fact, the set omega is thick, so this kind of inequality is true. This is exactly what is written here. In fact, it's exactly what I call the definition of what I call a Poisson set here, in fact. Okay. So why is this proof interesting? Because you see that there is a link between the Ludwig-Sereda uncertainty principle and the half-fit equation, in the sense that I defined before. So now it's time to go back to what we want to do. So in fact, if we go back to the observability inequality, one possible interpretation of this inequality is to say that it is related in some sense to the concentration of the solution. So what do I mean by that? In fact, this inequality can be understood as the solution are not too concentrated outside of the control region. So if you think, for instance, that you take B to be the characteristic function of little omega, if you have this kind of inequality, it means that you have enough information on little omega. Okay, so it means that in some sense, you don't have a sequence of solution that is concentrated too much outside of the control region. So it's exactly, in fact, the spirit of what I will present afterwards. So in fact, since there is a link between the half-fit equation and the Ludwig-Sereda uncertainty principle, what we will do, in fact, is that we will try to take as an initial condition some special function that is saturating the uncertainty principle. So saturating the uncertainty principle means that, in fact, this function, so that will be the prolate spheroidal wave function, in fact, will in fact be very concentrated somewhere, and of course it will be very concentrated outside of the control zone. Okay, and so what I expect is that if I take some initial condition that is quite concentrated outside of the control zone, if I am able to prove that it stays in some sense quite well concentrated in any time outside of the control zone, then I will be able to disprove my observability inequality because I don't have enough information in my control zone. Okay, so I will explain this afterwards. So what I would like to say is that, in fact, this result of non-controllability for the half-fit equation was already proved by Armand-Koenig. But here, in fact, I give in some sense a more constructive proof. And also what is interesting is that I am able to obtain a new result on the Grushin equation. Okay, so now it's time to present these prolate spheroidal wave functions. So how are they defined? It's very simple. In fact, they are defined as the eigenvector of some integral operator. So you just introduce what I call FC here. So you take a function which is in L2 of -1, and you just consider this function as a function of x. Okay, so of course FC is a compact operator, but you can also prove that it is a normal operator. So you can apply the spectral theorem for compact and normal operator. And so you can prove, in fact, also that all the eigenvalues are positive. So they are positive, and they, of course, they form a sequence that tend to 0. So you can prove that the largest eigenvalue, in fact, you only have an eigenspace of dimension 1. And so you can take one eigenvector that here will be normalized in L2 norm. And this is exactly what I will call the first prolate spheroidal wave function associated to the parameter C. And in fact, C here will tend to infinity, as we will see afterwards. Okay, so of course, by definition of an eigen function, this verifies this identity. And what is very interesting here is that, in fact, so you see that, in fact, Psi, just by making some change of variable here, you can see that Psi is in fact C band limited. And this is, of course, an entire function. In fact, it is an entire function of exponential type C because it is C band limited. Okay, and so you can extend, in fact, this identity to the whole complex plane by analytic continuation. Okay, so what is very interesting, in fact, for this function is So just to show you how behave this function. So you see that for C is equal to 1, the function is quite concentrated around 0. But in fact, if you take c is equal to 5, you see that the function is very, very small outside of -1, 1, and it's very concentrated in -1, 1. Okay, and this is exactly what will be interesting for the rest of the talk. So in fact, it seems that the concentration is exponential, and we will see that this is the case. In fact, so your function is very small outside of -1, 1, and it's very big in -1, 1. And in fact, you can prove a lot of things on this function. Notably, you see that here they are real on the real line. Of course, they are even, etc., etc. Okay. It's exactly what is written here. So you can also prove that there are no roots on -1, 1. And so from now on, I will assume that it is normalized in L2 of R norm, because you can extend this function to the whole line because it is an entire function. And I will assume that psi c is positive on -1, 1. Okay. And so what you can prove, in fact, and this is very important, is that in fact the integral of psi c outside of psi c square, sorry, outside of -1, 1 is equal to 1 minus mu c, where mu c is defined like that. So it just comes from, in fact, from this here and from some easy change of variables. And what is very important for the rest of the talk is that you have an asymptotic behavior, and you see that indeed outside of -1, 1 the function is very small. This is exponentially small. Okay, so it really means that this prolate is very concentrated on -1, 1. Okay, so this is the first important point. And so the second important point is that you have a link with the log-Vienneco-Serenda uncertainty principle. In fact, you can prove that if you take any other function which is C-band limited, which has L2 norm equal to 1, then in fact its integral, its L2 norm outside of -1, 1 is larger than 1 minus mu c. So what does it mean? It means that any other function concentrates less on outside of -1, 1. So it means that any other function concentrates, every other function concentrates less on -1, 1 because of this inequality. So what does it mean? It means that psi c is in fact the C-band limited function that concentrates the most on -1, 1. So you cannot find any other function that is concentrating more than psi c. And so you can prove, in fact, that this value 1 minus mu c, this is exactly the best constant in my Vienneco-Serenda uncertainty principle. I say something wrong. 1 over 1 minus mu c is the best constant for the Vienneco-Serenda uncertainty principle, in the sense that in the case where the thick set is the outside of -1, 1, the best constant that you can put here is 1 divided by 1 minus mu c. Okay, so it's something that is exponentially big, because 1 minus mu c is exponentially small, so 1 over 1 minus mu c is behaving like e to the power 2c, basically. Okay, another estimation that I would need here is the following one. So you can estimate psi c of 1, and you can prove that it's also very small, and you have an explicit equivalence for this quantity. It will be very important in the following. Okay, so the next important point is what is called the Lucky accident of Slepian. So in fact, this is very surprising, but if you introduce some appropriate degenerate differential operator that is written here, you can prove that FC and FC commute. So what does it mean? It means that psi c, so psi c, which was defined as an eigenvector of an integral operator, is also an eigenvector of a differential operator. And so you can prove, so you give a name to the eigenvalue that you call chi c. So you can prove that it behaves like C as C goes to infinity. And in fact, by analyticity, you can extend this equation as an equation in the whole complex plane. Okay, and in fact, this will be absolutely crucial in our proof, as we will see. And so this prolate spheroidal function, in fact, was introduced in some series of papers by Slepian, Landau, and Pollack in the 70s. And in fact, it has many applications, notably in signal processing, and you have some extension, and etc. Okay. So now it's time to present the results. So the result is the following. So I consider what I call the half-fit equation here, and I will take a very, very big control domain. The control domain of, in fact, the only thing that I assume is that its exterior contains an interval. So you can think basically that little omega is the exterior of a very small interval. Okay. So we have, of course, well-posedness in L2, and what I will prove here is that this system is not non-controllable, in the sense that for any time I can find an initial condition such that there is no control that will bring this initial condition to 0 in time capital T. So as I told you at the beginning, in fact, the non-controllability is equivalent to some appropriate observability inequality. So here, by duality, of course, the operator is self-adjoint, so you take exactly the same equation, but you remove the control. And so, in fact, so you introduce, so you look at your observability inequality. And so your observability inequality is exactly saying that this quantity is not going to 0 as C goes to infinity, if you take some family of initial conditions. So what I will do is that I will exhibit a family of initial conditions that depend on some parameter. I will introduce this quotient. And what I say is that if this quotient goes to 0 as C goes to infinity, of course, my observability inequality cannot hold. Okay, so this is the goal of the next part. Okay, so the first basic remark is that, in fact, you can prove that if you take as an initial condition the prolate spheroidal wave function that you translate in the Fourier variable by C, so it means that you multiply by an appropriate complex exponential, then in fact the solution in any time is just the complex, the extension on the upper half plane of the initial condition. So you can prove it by different means. The first means is just to make a direct computation, and another means is in fact to remark that if you take the half-fit equation for a function in the RD class, in fact, this is just the Cauchy-Riemann relation, and then it's quite obvious that that the solution is the extension in the upper complex plane. So another remark is that you can, in fact, reduce the problem in the sense that, of course, if you have controllability on some omega, then you have controllability on any larger set omega tilde. So by contraposition, if you have non-controllability on some large set, of course, you have non-controllability on any smaller set. Okay. And here, my hypothesis was that the exterior of omega contains a ball. So what does it mean? It means that after some translation argument, you can reduce, in fact, here you can reduce this problem, in fact, to prove the non-observability outside of a small interval. Okay, so I fix some epsilon, and I am going to prove some non-observability outside of this small interval. Okay, so to do that, I need really some precise estimations on my prolate spheroidal wave function. So the first one is the following. If you take a large x, positive t, and a large n of c, you can prove that you have this kind of estimation here. And in fact, the proof, so this is here that I really need to use my differential equation. So I introduce some adequate transformation of my prolate. Then I prove, in fact, that this phi c verifies some equation, which is written here. So you see that what is interesting is that you have only one term of order 2 or one term of order 0. And then, as soon as you have that, you can apply general estimates on complex second order ODEs. And then you make a lot of direct computation. And after a lot of work, in fact, you're able to prove something like that. Okay, so here I put the C in red for a good reason. It's because this term is very bad. This term is very bad because this term might be exponential in C. So it means that in some sense I have lost. I pretend that my initial condition is very well concentrated, let's say in -1, 1, but here I lose a lot of concentration in time, okay, because of this exponential term that will enter in competition with the 1 minus mu c, okay, the 1 minus mu c, which is exponentially small, okay. So here we can think that it's lost, but in fact this is not the case. So what I will do is that in fact I will not look at psi c on -1, 1, but I will look at psi c outside of some big interval, which is -c to the power 3/4, c to the power 3/4. And so if you do that, so you just take this expression here, you pass to the square, you integrate, and what you are able to prove is something like that. Okay. So here you have something that is exponentially small, and here you have something which can be exponentially large. But you see that if t is large enough, in fact, this term is bounded independently of c. Okay, so if I am able to take a t large enough depending on c, then this term will disappear, and I will have a very good concentration property, meaning that in any time my prolate stays well concentrated. And to do that is very easy. So in fact, the basic remark is that you have a natural scaling in the equation. And the natural scaling is that if you take any solution of the half-fit equation, the adjoint half-fit equation, so if you multiply the time on the space by some alpha, this is still a solution. So I will use this. In fact, so I will change a little bit my initial condition, and I will just multiply x by c to the power 3/4 divided by epsilon. Okay, and thanks to this remark, it means that you have a corresponding solution, which is given here. Okay, and you see that now what is interesting is that the time is really large. Okay, it's really large, and so in fact you have changed t into c to the power 3/4 t, and so you can prove, thanks to that, that you can get rid of this bad exponential term. And so just by making some change of variables and using the previous estimates, you can prove a very good concentration property that is written here. So with this initial condition, the L2 norm outside of -epsilon epsilon is very small. It's 1 minus mu c, which is exponentially small, in c to the power 3/2, and moreover you have 1 plus t, and this 1 plus t in fact is very important, not for the half-fit equation, but for the Grushin equation. So now, so this is in fact the numerator of my quotient. So now I need also a lower bound on the denominator of the quotient. And in fact, you can prove the following lower bound, which is written here. And this is very easy. So you use the Plancherel's theorem. Then you use the fact that U is a prolate. So you can use so you can use the fact that basically the prolate is equal to its Fourier transform up to dilatation. And so what you do is that you localize the integral you want to estimate around an adequate point, and then you are able to prove this kind of property. And here you also need to use a lot the differential equation. Okay, so that's why this differential equation is very important. And at the end of the day, so what do you obtain? You obtain something like that, just by making the quotient between these two quantities. Okay. And now I use my asymptotic behavior of the 1 minus mu c and of psi c of 1. And here there is a big miracle that happens. The big miracle is that the exponential here, of course, are disappearing. And here you have, if you look well, you have 1 over c. But in front, I have c to the power 3/4. Okay, so at the end of the day, I have some constant divided by c to the power 1/4. And so it goes to 0 as c goes to infinity. So my quotient is going to 0 as c goes to infinity. And so my observability inequality is disproved. I will just explain rapidly what is happening for the Grushin equation. Okay, so what is the Grushin equation? This is in fact a degenerate equation posed on the plane. So here I am working on the whole plane, and I am considering this kind of degenerate parabolic equation. And in fact, you see that you have a degeneracy here at x is equal to 0. So what does it mean? It means that you are elliptic outside of f is equal to 0, but for x is equal to 0, you are losing the direction y. Okay. So in fact, you can prove very easily that this is still a hypoelliptic equation, but it's not very interesting for what I need. And here, what I take as control domain is in fact the exterior of a very small band, horizontal band. Okay. And what I am able to prove here is that this system is also not non-controllable in no time capital T. And so what is new here? So there is a lot of literature on this equation, in fact. And what is new here is that the fact that you can take y, which is on the whole real line. And on all the other results, y has to be on a bounded interval. Okay. And the remark is the following. So you look at, so you try the same strategy. So you look at the adjoint equation, which is the same. And in fact, you take the Fourier transform in the second variable, in the variable y. Sorry, there is a typo here. It should be a psi. And what you remark that in fact now this operator, it's exactly, in fact, the harmonic operator. And so you know the eigenvectors of the harmonic oscillator. It's a Hermite function, and the first one is in fact is a Gaussian. So it's written here. And as soon as you remark that, in fact, you can consider an appropriate solution of the Grushin equation. And in fact, after some computation, you remark that in fact, if you take, in fact, this solution is exactly a solution of the half-fit equation where you have changed the time in some sense. So meaning that if you change t into t plus x2 over 2, then in fact, this is a solution of the Grushin equation. Okay. And now you are very happy, in fact, because you can use exactly all the estimation that I gave for the half-fit equation. And it's here that I really need to use my 1 over 1 plus t in my upper bound for the numerator, because it gives you a little bit of integrability, in fact, in x. And so by doing exactly the same strategy and almost exactly the same estimation, you can also prove that this quotient is going to 0 as c goes to infinity and exactly at the same rate. And you see it's really free, sorry, because in some sense I have reduced my problem to the half-fit equation. So even in itself, this remark is quite interesting, meaning that you can reduce the problem for the parabolic degenerate parabolic equation to a problem for the half-fit equation. Okay, so it's time to conclude. So here, so one drawback, in fact, of my result is that it's only a one-dimensional result. But in fact, you can try also to do the same for a multidimensional half-fit equation. And in fact, there are also some notion of prolate spheroidal wave function in RD. And notably, what will be interesting is to consider, in fact, radial prolate spheroidal wave function, meaning that you take a Euclidean ball of RD as a support. And then you still have nice properties. Notably, you still have a differential equation for this multidimensional prolate spheroidal wave function. So another interesting case would be to consider the case where x is bounded and y is not bounded for the Grushin equation. So I don't know how to do that. And also it would be very interesting to characterize the initial conditions that cannot be brought to 0, because here, if you remember well, what I do is that I use the observability inequality. So I am able to say that the observability inequality is false, but I am not able to find explicitly one initial condition that cannot be brought to 0. And the long-term goals, in fact, is, can we use this general method, in fact, so meaning you consider some set, and you would like to understand if by saturating some appropriate uncertainty principle, you are able to create counterexample to controllability in the case of a weak diffusion. So weak meaning either Grushin or half-fit equation. But of course, if you try to generalize in other geometries than RD, you need to get rid of the Fourier transform. And so it means that you need to understand what kind of uncertainty principle you need to prove, and this uncertainty principle, of course, you need it to be different because you don't have access to the Fourier transform in general geometries. And I have finished, so I thank you for your attention.
Thank you, Pierre, for your talk. Any questions or comments?
Yeah, so, hello. Hi.
Hello. Hi.
How are you?
I'm
Hope
fine,
everything okay. Congratulations. Very nice talk. Just a question. You hope this can be, because of course you are using Fourier transform, but your hope is to extend this to for more general hyperelliptic operators, I guess, right? Or
yes. The problem is that here I really use I really use this magical formula, in fact. And of course, this magical formula is only true if you take exactly x squared, for sure. So, okay, yeah. For instance, if I take the Grushin operator and I replace x squared by q of x with q of x, which is behaving like x squared, I don't know how to do. So maybe it's possible to, because so this expression is not true, but maybe it's not so far from the reality. You see, so maybe by trying to make some approximation or something like that, maybe it will be possible to say something. But I don't know. No, the problem is, in fact, even for the half-it equation, if you don't consider RD, but if you consider some general domain, you don't have the Fourier transform. But in fact, the Fourier transform here, what is important is that the Fourier transform is somehow so the Fourier transform is somehow related to the half-it operator, because the projection in low frequency, this is exactly the special projection for the half Laplace operator. Okay, so my hope would be to obtain some uncertainty principle for projections of the half-it operator on general geometries, something like that.
For instance, Pierre, because so you are taking a Laplacian half of the Laplacian, let's say. So if you take 1/4 of the Laplacian, do you believe?
This is already known. Sorry, maybe I didn't. Okay, maybe I have not insisted very much, but this is exactly the. Sorry. Yeah, in fact, the half Laplacian, this is exactly the critical value.
Okay, yeah.
If you are higher, you are controllable, and if you are lower.
No, yeah, but my question is, if you take the Laplacian 1/4, right. Of course you know, of course, but I mean, what that would, if there is a way to translate somehow to some equation as you did for the Grushin.
This is a good question. The problem is that here I already use a lot of complex analysis. In fact, what I use here very crucially is this expression, and of course this expression is not true if you are not taking the half-it operator. So in fact, yeah, in this case, because yeah, this is a crucial point. The crucial point is that you still have a prolate that is extended in the complex plane, and if you take another operator, you don't have this nice formula. So in fact, I don't know what to do in this case.
Okay, thank you.
Any more question or comment? Pierre, just a small question. I don't know if it's a silly question. I'm sorry. If, in this case, in this particular case you are working, what can we say about the approximate controllability? It's
true. Yeah, it's true. The unique continuation is true. Yes.
Okay.
And it's not very difficult to prove, in fact, because
to see that.
In fact, any solution will be the sum of an entire function and an anti-entire function. So you take
for any power of the fraction.
No, I mean for this half-it equation, it's true, and it's not very difficult to prove. And I think that is true for any power of the Laplace operator. But
okay.
Maybe I'm not able to give you the precise argument, but I think it's true. Yes, for any power, any positive power.
Okay, thank you. So Pierre, thank you again for your wonderful talk, and I hope that we can see each other soon enough.
Okay, thank you very much.
Thank you. Juan?
Oh, thank you, Mauricio, and thank you a lot, Professor Pierre Lissy, for your excellent lecture.